Hi there. We're going to continue with our section 9.3 discussion here by dealing with this example 3. We're testing a series for convergence. And you'll notice we just talked about the P series and the harmonic series, and I'd like to kind of point out within the context of this problem the connection that we've got between it. Now, if you take a look at this particular summation, the summation from 2 to infinity of 1 over n times the natural log of n, one thing I'd like to point out here initially is the fact that, yes, indeed, we are starting at an n value of 2. And I don't want that to be bothersome for any of you, because think about it for just a moment. If you decided that you wanted to start at n equal 1, you were going to have big problems because the natural log of 1 here is going to be 0, and you would have a term that's defined to start off your series. Well, if you want to look at this just for a little bit, you'll probably take note of something that's very interesting. There's a portion of this summation that you have a lot of information about. And what I'm speaking of specifically is the 1 over n portion. We know that the summation of 1 over n, as n goes from 2 to infinity, diverges. And the reason we know that is because 1 over n is called the harmonic series, and we have that from a previous definition, that the fact that it diverges. But the question that we're asking ourselves now is, what if the denominator grows bigger? Well, it's pretty clear that that's what's going to happen. You've got this other component, natural log of n, sitting alongside the n, and that's going to make that denominator get bigger and bigger, as of course n gets bigger and bigger. And the thinking is, if that is the case, denominators growing larger, that means our terms themselves are growing smaller, and thus we have the potential for convergence. Now, what you're going to want to be real careful about here is making assumptions like this. We're going to find out in just a moment whether this series will converge or diverge. And you're going to see how the tests that you've learned up to this point become very important. Sometimes you just can't use intuition, such as the type that I mentioned a moment ago, to determine convergence or divergence of a series. All right. Well, if you take a look at this, it's pretty clear that this is not going to be a geometric series. It's definitely not a P series all to itself. And I think it's pretty clear that the nth term test won't work. Now, to review the nth term test here very briefly, you would take the limit of your nth term here, 1 over n ln of n, as n approaches infinity, and you'll find out that you get to 1 over infinity pretty quickly, which of course is 0. And if the nth term test gives you a result of 0, you can't really conclude anything about the behavior of the series. So that really leaves you up to this point in section 9.3 with one type of test, and that would be the integral test, which is the test that we learned at the beginning part of this section. Now remember, in order to use the integral test, you've got to make sure that the groundwork is laid for its use, and that is the 3 criteria are met. Criteria 1, is this function positive? Well, we'll just temporarily rewrite the nth term as a function, and I'll just use the variable x just because you're probably more comfortable with it. And if we look at that for just a little bit and we try to plug in x values that would be 2 and bigger, we'll find out that we certainly are going to be larger than 0 for x values that are 2 and larger. All right, so we are positive. The next thing that we ask ourselves, are we continuous? Well, you're not going to have any continuity issues here with this denominator for x being larger than or equal to 2. The only continuity problems that we would have would be at x values of 0 and 1, and we were not going to use those in our interval anyway. So we'll just simply state that yes, indeed, f of x is continuous. For those values of x. Now, the third and final criteria that must be met is the fact that the function must be decreasing on the interval. And typically this is going to take just a little bit more time because you're going to have to rely on the derivative test, the first derivative test. So we'll take a derivative here, and you can go about the derivative in a variety of ways. You can use a product rule with a chain rule component. You could use the quotient rule here with a chain rule component. I'm just going to leave this written as it is, and we'll just go ahead and approach it from a straight up quotient rule. So the derivative of the top is 0, which means that multiplying, I guess, by the denominator is sort of a moot point here, as it's all going to cancel. And then I'll subtract the numerator. Now I'll multiply by the derivative of the denominator, and this is probably where we've got our most difficult work, because we'll have to use a product rule here. So the derivative of x is 1 multiplied by ln of x. Add to that x multiplied by the derivative of ln of x. And then since this was indeed a quotient rule, we'll have to put this expression all over the natural log of x squared. I would go ahead and take a moment to simplify things just a little bit, and basically you'll arrive at this result here: negative quantity, the natural log of x, plus a 1 all over the natural log of x squared. I want to be very careful. The numerator quantity doesn't suggest that we're taking the natural log of the quantity x plus 1. It would just be the natural log of x with a 1 added afterwards, and then of course it's made to be negative. And I think this really tells us all that we need to know. This guy right here. You know, think about it. You're going to be plugging in values of x that are 2 or bigger. That's going to make everything in the parentheses upstairs positive. Everything in the parentheses downstairs is going to be positive regardless because of the square. But that negative out in front is going to turn everything negative, and we've got pretty much the result that we had hoped for. So you could go ahead and finish it off by saying that f prime of x is less than 0 for x greater than or equal to 2. So that means that we are going to be decreasing. So all that work just to tell us that, yeah, now you can really start the problem. You can go ahead and use the integral test. So if you recall, the integral test just simply states that the behavior of the integration from the lower bound to the upper bound, 2 to infinity in this case, of this function will behave the exact same way as the series would. So really what separates you and the solution to this problem is a topic from Chapter 8, once again, called Improper Integrals. I think it was in section 8.7, I believe. So in order to integrate this and to really do it the correct way, we need to remember that the laws of calculus don't really allow us to use infinity as a boundary. So it becomes imperative to rewrite this as an integration problem with a limit statement out in front. I'll use b as an upper boundary. Once again, it never really matters what the variable you choose. And in the process of integrating this, we're going to have to think about a potential u substitution here. You see this integral from time to time, especially on the AP exam, and it's not meant to be tricky. It really is meant to be pretty straightforward. If you think about it just a little bit, the u that you're going to use is going to be the ln of x. Now, why would that be the case? Well, if you take the derivative of that u with respect to x, you would get 1 over x. And that's pretty much exactly what you were hoping for here, because 1 over x is present in the integrand. So when all comes down to it, what you're doing in this problem essentially is just integrating a 1 over u form with respect to u. Okay, now what is that going to do for us? We're going to still have our limit out in front. The integration of 1 over u is the natural log of the absolute value of u. And you'll notice our u here is kind of interesting. It is the natural log of x. So you've essentially got the natural log of the absolute value of the natural log. Evaluate from b to 2. Well, we'll go ahead and plug in our boundaries b and 2, and we find out that we've got the natural log of the natural log of b in absolute values minus the natural log of the absolute value of the natural log of 2. Now the absolute values, I guess, weren't so required in the second expression here, since the natural log of 2 is going to be positive. But you're going to see very quickly that this has a very clear solution, because when you take this limit and you allow b to grow very large and unbounded, this portion right here is going to become very large. The natural log of infinity is essentially going to be infinity. And then, once again, the natural log of infinity will be infinity again. Now, I don't want to pretend like I know what the natural log of the natural log of 2 is, but it's some constant. But that constant is pretty much going to be meaningless when it's subtracted from infinity. So if you recall, if an improper integral yields an answer of infinity, we would say that it diverges. So if the improper integral diverges, then that says that our series will have the same behavior, thus divergent. There's no question that the integral test is probably going to be one of the more time-consuming tests that you perform. But the good news is once you get things rolling with the integration, provided that you can find the integral somewhat easily, it doesn't take too long for you to realize the convergence or the divergence. So in that regard, it becomes a pretty powerful test, and it does work on quite a few of the series that you would encounter.